last 5 classes we talked about process of solidification and particularly with reference to I mean in general, I mean two hypothetical metals A and B, and how they solidify, form a metal, and how do we interpret its structure, and what is the effect of composition on the structure, and we also talked about several invariant reactions, but all these were discussed in general using hypothetical cases. Today, we look at one specific phase diagram, that is called iron carbon phase diagram, and we will see that with iron with carbon forms a compound called carbide, that is iron carbide, which is known as cementite. And in fact, the first diagram that we will talk about is actually iron carbide phase diagram, and this forms the very basis of or describes the formation of the structure or of one of the most commonly used material by human being, that is steel. And let us see that under this chapter, that is iron carbon phase diagram, we will look at that allotropic transformation. Iron exists in several crystalline form, and carbon can dissolve in these lattice of iron, and this solubility is a function of crystal structure and temperature. And we also will talk about a cementite phase, which is iron carbide. It has a definite composition, and because of the limited solubility of carbon in iron, and in the iron carbon phase diagram we do get several invariant reactions. We will look at them. We will look at iron cementite phase diagram to start with. Later on we will also talk about that iron graphite phase diagram, because graphite is the most stable phase of carbon, and so how does this diagram changes when cementite breaks down to graphite. We will also talk about the evolution of microstructures in steel, and we will know about the difference between steel and cast iron, and we will have a passing comment on effect of cooling rate. Although the equilibrium diagram just describes the structural evolution under very slow rate of cooling, nevertheless, we will see that how this gets changed with or how do we take into account effect of cooling rate on microstructure. Now, if you look at say suppose if you take molten iron or take iron in a crucible, melt it, heat it to let us say 1550 degree centigrade, and then you let it cool very slowly and measure the temperature. And if you measure and if you make a plot of this temperature as a function of time, you will find that in the cooling curve you will get a number of steps. These steps represent equilibrium between the liquid, say this one first one between liquid and solid, and this here step represents equilibrium between two solid phase, and this also represents an equilibrium between two solid phases. So, the transformation that it goes through is first it solidifies, the liquid solidifies into a crystalline structure and it is body centered cubic. Next, at a little lower temperature, say this 1394, this body centered cubic structure gets converted into face centered cubic structure. Again, this face centered cubic structure gets converted into a body centered cubic structure. So, you have a high temperature BCC structure, you have a low temperature body centered cubic structure. And if you cool further below, that initially that BCC structure, this does not exhibit magnetic property, it is paramagnetic, it is and if you cool below a temperature called Curie temperature, that is around 770 degrees centigrade, below this it is ferromagnetic in nature. But here it does not have any any that enthalpy change is negligible. So, therefore, that you do not get any step here, but if you measure magnetic property you do find a change. So, that way you can say as you heat iron from room temperature to its melting point, it will convert from ferromagnetic state to paramagnetic state at Curie temperature. Then from paramagnetic BCC crystal structure, it gets converted into a face centered cubic. Again at 1394, it gets converted into a body centered cubic structure, and then melting takes place at 1539. Now, the solubility of carbon, and if you add carbon, of course, this cooling curve will change. And how does it change? This will depend on the extent of solubility of carbon in iron, and this solubility depends on the crystal structure as well as the temperature. Now, the question comes, where is the carbon atom located? If dissolves in iron, where will the carbon atom go? And this is shown in the next diagram. So, this is a body centered cubic structure. If it is a body centered cubic structure, then this large spheres, they represent location of iron atom. So, this is a BCC structure. So, you have one atom at the corner of the cell, one at the center of the cell, and with these red dots, these locations of interstitial sites have been represented. Say this, they represent possible locations where a carbon atom can go. So, these in a BCC structure, if you recall your earlier lecture, that the atoms touch, they are arranged in such a way that along the diagonal direction they touch each other, and we did calculate the dimension of the interstitial spacings. So, here you will find that interstitial, the gap, these sites, they are called octahedral sites, and octahedral sites, then if you look at this paper here, these are called octahedral site, octahedral sites, and you see that one dimension, see, is in this direction, so we can say one dimension is this direction. This gap is much smaller than the gap in this directions. So, they are all identical site. If you join these, and similarly if you visualize, there is another cell on the top, and you can join these with the center atom on the unit cell above this, then you will get an octahedron, and that center of that octahedron is the likely location of carbon atom. And here if you count that number of sites, you will find that you have 6 faces. So, each face is shared by 2 unit cells. So, contribution of this face center, it is 6 over 2, and then you also have edges, and you have 12 edges. So, 12 edges, but each edge you can have, along each edge you can have 4 such unit cells. So, contribution of this is 12 plus 4. So, this comes out to be, this is 3 plus 3, that is 6, and BCC lattice, you have 2 atoms per lattice. So, you have likely interstitial site is 6 per unit cell, and iron atom you have 2. So, every one iron atom you have 3 interstitial site, whereas if you look at face centered cubic structure, here also these are called octahedral sites, which are the center of the edges. And here if you try and join and make this octahedron. So, you look at, so this is at the center of the octahedron, you have this is the center of that octahedron, you can join, and similarly you can join this, you get an octahedron. But the difference here is this octahedron, it is same, I mean this is a regular, I mean that this dimension of in this direction and this interstitial gap in this direction, they are identical. And here if you try and calculate the number of interstitial site, what you have? You have 1 at the center and you have 12 center of 12 edges, and for each edge on each edge you can have 4 unit cells. So, its contribution is 1/4 and this will add up to 4, and in FCC lattice you have 4 iron atom per unit cell. So, here you have 1 atom or 1 site per atom, here you have 3 sites per atom. So, obviously, even though we know that BCC structure is not as close packed as face centered cubic. Face centered cubic, this is also called close packed structure. This is has the maximum packing density, close packed structure. This has maximum packing density, but although the packing density is higher, the gaps whatever you have, those gaps are larger, because you have 1 site per atom and here you have 3 sites per atom. So, that gaps, even though you have total void space is more here, that gets distributed amongst more number of sites. So, that is why here true that you have more open space, but the dimension of the space, the shortest dimension, if a carbon atom goes here, it will push up, unless these atoms are pushed apart, it may not be able to move into the site. So, that is why in BCC the solubility of carbon is very limited, whereas in face centered cubic structure the solubility of carbon is much higher. And so, this is why you will have, as you cool the solidified metals initially, even if BCC structure has formed, and later on when it converts into FCC, it can accommodate more number of carbon atom. So, there will be some kind of transformations which will involve which may involve 3 phases, and therefore, what you have in the iron carbon diagram, you will have 3 invariant reactions which are listed in this slide. So, these are the 3 invariant reactions. So, you have look at here the delta, phase delta is BCC, and phase if I look at it here, this is the first phase which comes out, this is body centered cubic, and here this delta reacts with a liquid and will give you austenite. This is called gamma. This has face centered cubic structure, and these are very commonly known as, this solid solution is commonly known as austenite, and BCC structure is known as ferrite, and this is called delta ferrite. This is the high temperature form of body centered cubic iron. So, this you can say that this is delta ferrite. So, this is austenite, and this 3 phase reaction takes place at 1495 degree centigrade, and this reaction, if you recollect your lecture. So, here this liquid reacts with solid, giving another solid, and mark here that carbon content are fixed, because this is a 3 phase equilibrium. So, they will have definite composition. So, now here look at it, here gamma, it has a much higher carbon content than that of ferrite. So, this is because it can dissolve more amount of carbon, and this is weight percentage, and this reaction is called, first one is called peritectic reaction isotherm. And next, at a little lower temperature at 1145, there is another reaction taking place. This is that liquid having a fixed carbon, that is 4.3% carbon, definite carbon content, breaks down into mixture of 2 phases. This is gamma, which is called austenite, and look at it, here carbon content is around 2%, and a carbide which has a definite composition is Fe3C. So, iron 3 atoms of iron and 1 atom of carbon, Fe3C. This is carbon content comes out to be 6.67% carbon, and this is called cementite. This Fe3C is called cementite, and this reaction is eutectic reaction. This invariant reaction is the eutectic reaction, and product is eutectic, and this product also has a definite name, that eutectic is iron carbon phase diagram. It is labeled as, or it is known as ledeborite. This will be an intimate mixture of austenite and cementite. And the third reaction, which takes place around 723 or 727, around this temperature, this is a fixed temperature. Here that austenite of a definite composition, that is 0.8% carbon, breaks down into a mixture of ferrite and cementite. Look at this ferrite, this has even lower carbon content than this. So, this is at a high temperature. At a higher temperature, lattice parameter also will be larger. So, its atomic, the interstitial gap also is higher. So, here the solubility is little less, but look at the solubility here in ferrite. This is the low temperature ferrite. This has a body centered cubic structure, and here this austenite of 0.8% carbon breaks down into a mixture of ferrite and cementite, and this reaction is called a solid breaking down into a mixture of 2 solid. So, this is called, this reaction is called eutectoid reaction, and the product that we get, this type of structure, that is known as perlite. And now, let us see with this information how can we construct that phase diagram, which is shown here. So, this is that peritectic reaction. So, here you have, this is the region which is delta, here you have liquid, delta plus liquid, and delta plus liquid reacts here, and this is the peritectic reaction isotherm. this is the peritectic reaction isotherm, and here this is 0.08% carbon, and then this reacts with liquid. This has, let us say, 0.55% carbon, and then it gives austenite of this composition, which has 0.18% carbon. And here when this reacts, you get gamma, and if it is on the other side, right hand side of this, you get gamma plus liquid. That means, here if it is on the right hand side, amount of delta which has precipitated out, amount is so less that even if it reacts with liquid, the entire liquid is not consumed, some amount of liquid is left, and that remaining liquid solidifies into austenite. Whereas, on this side, amount of gamma is so large, delta is amount of, on left hand side of this peritectic point, amount of delta is so large that entire liquid gets consumed, and what you have here in this region, you will have delta plus gamma. Gamma forms, but some amount of delta remains. So, likewise this part you will have, this is the gamma plus liquid, and this side you will have liquid. From liquid, cementite will precipitate out, and this cementite, let us see, this is composition, this diagram, this represent 6.67% carbon. So, that means, this line represent cementite, and this is called, this isotherm is called eutectic, and same terminology is followed. On the left hand side of the eutectic, that alloy is called hypoeutectic. On the right hand side of the eutectic composition, alloy is called hypereutectic. So, here this part, your structure will be gamma plus eutectic. So, this eutectic is known as ledeborite, and this side you will have primary cementite plus ledeborite, that is eutectic. Now, what happens on this side? This side gamma, if you cool here at this temperature, that is around 723 degree centigrade, this is the other isotherm, and this isotherm is, this is the eutectoid isotherm. Eutectoid isotherm, and here that gamma here reacts, and we give you and will give you an eutectoid structure, and this eutectoid structure we said is called perlite. And the alloy on the left hand side here until this point is called hypoeutectoid, and the alloy from right hand side of this is called hypereutectoid, and in this case the structure will be that you can reason out as gamma. Here it gives you perlitic structure, here from gamma some amount of alpha will precipitate out. So, this alpha is called, which precipitates out before eutectoid temperature, is called pro-eutectoid alpha. Similarly, on this side from austenite, as you cool, here you will have cementite. So, at room temperature between, and this maximum solubility, this is around 0.02. So, between this and this you have hypoeutectoid still, where the structure will be ferrite plus perlite, and here the structure will be perlite plus proeutectoid cementite, and here what happens, there is austenite here. As you cool down, this austenite composition also will follow, will change, and this change will be given by this line. This represents solubility of carbon in austenite. As the temperature goes down, the solubility decreases. Now, here just before this eutectoid reaction, now you have certain amount of leadiborite, which is a mixture of austenite and cementite. And what happens here, that austenite in leadiborite will transform into perlite. So, what you will have here, you will have some proeutectoid cementite. When this, because the solubility of carbon decreases, some amount of cementite will precipitate out from austenite. Then you will have that entire austenite, whatever remaining austenite will convert into perlite, and then you have leadiborite structure. I will represent leadiborite is a LD, and which is a leadiborite. Before this, it was a made up of, before eutectoid reaction, it was made up of austenite plus cementite. So, what happens, this austenite, from which some amount of cementite will precipitate out as you cool down from here downward, and balance austenite will again convert into perlite. So, what you have at room temperature is called transformed leadiborite, say where, which will be made up of a relatively intimate mixture of perlite and cementite. Similarly, on this side you will have cementite, and then you will have leadiborite, which is transformed leadiborite. So, which will be made up of perlite plus cementite. So, this gives this diagram, therefore, gives you a picture of what type of structure you are likely to get at room temperature in an iron carbon alloy. As you increase amount of carbon, let us say from very small amount to a very large amount. When it is nearly 0, it will be pure ferrite, say like here, it is a single phase structure, and when it exceeds a particular amount, you will get some amount of perlite, ferrite plus perlite. Then when it exceeds 0.8% carbon, it will be perlite plus cementite. When you go beyond this 2%, then you will get the transformed eutectic also will appear. Transform eutectic and some amount of austenite, which has been transformed into perlite. So, this is the type of structure, and here you will get cementite and transformed leadiborite. So, that means as carbon content is changed from 0 to 6.6, you get a significant change in the microstructure from pure ferrite, that means pure iron, to an extreme case, that is iron carbide. So, this diagram, if you look at, this is the phase diagram, and here what we say, this alloys which are containing up to 2% is usually said, where you do not get any eutectic structure. This part of the diagram we call steel, this represents the composition of steel, whereas if you go beyond 2%, this portion of the diagram represents cast iron. As we will go by, we will see this type of cast iron, where you have substantial amount is known as white cast iron. And later on we will see that as you increase the carbon content in the alloy, the stability of that cementite decreases, and it can get converted into decomposed into iron and graphite. So, that time the diagram will change slightly and we will come to it little later, but let us for the time being concentrate on this particular type of diagram. This is also known as iron cementite phase diagram, or you can say the cementite phase here. This diagram, this represents cementite. It is also known as Fe3C carbon iron carbide phase diagram, and this we say that this is a phase which is called metastable phase. It is crystalline, it has a complex cubic structure with a very large number of atoms. Unlike pure metal, where in BCC you have only 2 atoms per unit cell, here you will have large number of atom per unit cell. It has a little complex structure, but let us not go into the details of that. This is its behavior wise, its behavior, your melting characteristic will be exactly like a compound, pure compound. So, we can say this is some kind of a compound like of structure, and we call this is called cementite. Now, let us look at the structure that you get when you cool an alloy containing 0.8% carbon, and this alloy is called an eutectoid steel, or this iron carbon alloy is called eutectoid steel. And what will be its cooling curve? Looking at its phase diagram, it is very easy to construct its cooling curve. You will get an inflection here, and this is the region where solidification takes place, that from liquid gamma precipitates out. Here solidification is complete, you have gamma, and at this eutectoid isotherm, this gamma decomposes into a mixture of ferrite and cementite, and let us see what will be its structure look like. Now, here let us say in this particular case, as solidification proceeds, you will have gamma precipitating out, you may have some gamma here also, gamma some precipitating out, and finally, it will be entirely filled up by gamma. All these are gamma grains, austenite grains. And now, at this temperature what happens? Say suppose you cool it slightly, what will happen? Here first some carbide may precipitate out with, let us say, suppose we take carbide precipitating out here like this. This is a carbide is precipitating out, and carbide takes up very large amount of carbon, that is 6.67% carbon. So, the surrounding region will get depleted of carbon. So, when it gets depleted, another plate of very low carbon area will form. So, this is called, so this is cementite. Let us say the dark line is cementite and this white area, this is ferrite, that bright area is ferrite, and this is how when this ferrite precipitates out, from this carbon will get rejected, and when it gets rejected, it goes to the interface, and here again a plate of cementite nucleates, and this is the way the process will continue, and ultimately what you find, you will get this kind of the entire area, it gets converted into this type of a lamellar eutectoid structure. So, this is called, this type of structure is called perlite lamellar structure, and this is shown pictorially here. This is shown the mechanism, say when a platelet of cementite forms, it rejects, it takes lot of carbon from the neighboring area. So, this area the carbon gets carbon depleted. So, a ferrite platelet nucleates, and this is the way it progresses, and which is shown here something like this. This is how this paralitic structure develops. Now, we have seen during that discussing phase diagram that it is possible to calculate the amount of phases which are present in the structure. Say suppose here once you have cooled below this eutectoid temperature, let us say 723 degree centigrade, then what will be the amount of percentage carbide in this structure? Now, here you can apply lever rule, and apply lever rule that amount of just below this eutectoid temperature, you can say that amount of cementite will be proportional to this part, that is cementite over ferrite. This will be proportional to the cementite is proportional to this area, that is A B. Ferrite part will be proportional to this area, that is B C. This is the lever rule, and if you recollect the lever rule, you can apply and try and find out what is the percentage carbide here. So, this will be A B, and if we neglect this, if we say this point is 0.02. So, for practical purposes, if you neglect this, then you can say that this amount will be amount of carbide will be A B by A C times 100 percentage. If you want to calculate this time 100, this will be around 0.8 over 6.67, and you can calculate it out, and it may come around 14%. So, if you look at that microstructure, what you will find in this microstructure, this type of paralytic phases, that structure, you will find the around approximately this is comes out to be 14%, means you can say 1:7. And if we make an assumption that density of ferrite and carbide, they are nearly same. So, this will also represent the volume percentage, and volume percentage is what when you see when you look at the microstructure. So, this part, this is the width of ferrite plate. So, this if this is 7, this width of cementite plate will be around 1:7. So, you get a lamella. So, that means paralite, that eutectoid structure, it is a lamellar structure, and the two phases are present in the ratio 1:7. So, in the same way, I leave it to you to find out the microstructure that will develop if for a hypoeutectoid steel, anything between 0.02 to 0.8, and this you can clearly see that here apart from that eutectoid structure, you will have some amount of ferrite precipitating out as this temperature, as the in this temperature zone from here to here. That means, this is a critical temperature, you can say, where from austenite some amount of cementite, some amount of ferrite will precipitate out, and if ferrite precipitates out, austenite will get richer in carbon, and austenite composition will change along this line until you reach that eutectoid isotherm, where you will have ferrite but virtually no carbon, and another you have austenite where you have all the carbon, that means around 0.8% carbon. So, here what you have is this is the point. So, that means over here until this you have this type of structure, you have grains of austenite, and here you will have, when this temperature goes below this, you will have some ferrite grains nucleating in the grain boundary.
So, you will have from ferrite grains nucleating here, the grain boundary. These are the pro-eutectoid ferrite, and when that eutectoid temperature, this temperature is reached, you will still have some amount of austenite left, and the balance austenite will transform into parlitic structure. So, you will have this kind of microstructure. So, this is the case of a hypoeutectoid steel. In the same way, you can do it, estimate. Now, you can also estimate here. Just now we estimated amount of cementite in a eutectoid structure. Now, here in this structure, say suppose if this is the composition, and here you have the structure will consist of ferrite plus perlite. How do you find out percentage perlite? Perlite has 0.8% carbon, which is represented by this point C. And here, so therefore, percentage perlite will be equal to perlite will be amount of perlite will be proportional to this region. So, that means A, B, and this entire region is A, C. So, if it is around if carbon content is around 0.4, this percentage perlite will come out to be 0.4 over 0.8. So, around that means 50% perlite. Similarly, you can calculate ferrite, amount of ferrite will be B c over A c. Now, it is also possible that you can find out the total amount of cementite. Total amount of cementite here is just the cementite is present only within the eutectoid structure, and I leave it to you to find out what is the amount of percentage cementite. Here also you will apply the lever rule, and cementite composition is given by this point, and you say that ferrite, you ignore the solubility of carbon. So, ferrite composition is given by this point, and this is the composition of the steel. Now, how about the structure of a hypoeutectoid steel? Now, here it will also follow, I mean the process of transformation will be exactly similar to one that we considered in the case of hypoeutectoid steel. Now, here again that cementite will start precipitating out at the temperature, say until here it is normal solidification, which we have seen in most cases. So, in this temperature region, here the solidification is complete, you have austenite. So, these are the austenite grains, and when cementite starts precipitating out, always it is the grain boundary where the amount of cementite will form, and cementite is a tendency it will form along the grain boundary. So, it is a possible that you will get the cementite forming in this grain boundary region. This is the pro-eutectoid cementite, and all this process of precipitation of cementite along the grain boundary takes place in this temperature range, and once that eutectoid temperature is reached, because as this temperature goes down, the composition of austenite changes along this. So, then austenite becomes less rich in carbon, and ultimately when it reaches this point 0.8%, then both cementite and ferrite start precipitating out simultaneously, and you have perlite formation in this zone. So, you will have this kind of structure. You will have a network, you will have perlitic region. So, perlite is not a phase, it is a mixture, intimate mixture of two phases, that is cementite and ferrite. These are the intimate mixture of two phases. So, line I am representing, this line represents cementite, that white region represents ferrite, that white portion represents ferrite. And here also I will leave it to you to calculate the amount of the different phases in hypereutectoid steels. Now, let us look at the structure of the eutectic, that is solidification of that eutectic, that means over here. Now, here the cooling curve will look like this. You will have one isotherm here, this is the eutectic, and another isotherm here, this is eutectoid. So, here you have liquid, here you will have austenite, and as the temperature goes down from the here you will have an intimate mixture of austenite and cementite, that is eutectic structure, and eutectic will be a mixture of, let us say that eutectic will be a mixture of austenite and surrounded by. So, these are austenitic region, and so you will have intimate mixture of austenite and cementite. And this, from this austenite, as the temperature goes down, because the solubility of carbon in austenite goes down, amount of cementite will come out. So, when it reaches this temperature, you will have even more amount of, so amount of these austenitic region, they will shrink, and more amount of carbon will precipitate as cementite. So, this area is cementite. So, here whatever amount of austenite you had at eutectic, which is shown over here. So, at this eutectic temperature you can calculate that amount of eutectic. This is amount of austenite in eutectic, this is d E over C E. An amount of, but when you cool further, what happens? Here you have austenite, its composition has changed. Initially it was 2% carbon, now this austenite carbon is 0.8% carbon, and this is cementite. Now, this austenite gets converted into perlite. So, you have perlite, you can find out how much is the amount of perlitic region in the eutectic, and this will be given by perlite amount will be d E over this entire amount is B E. So, here I think I just explained. So, here you have that at eutectic temperature, here your structure will be this will be your austenitic region. So, these are your austenite, this is cementite, and as the temperature goes down from this austenite, cementite precipitates out. So, they become smaller, they become smaller, and at eutectoid temperature this is cementite, which has a definite carbon content 6.67, and you have some of these austenite with carbon content 0.8%. Now, as you cool down further, this austenite gets converted into perlite. So, you have this lamellar structure. And it will be more. So, and this percentages can be estimated using lever rule. So, this is called transformed lead boride. So, what you will have really, you will have some areas which in this microstructure which will appear like intimate mixture. You will have parlitic region and which will be surrounded by cementite. And so, this is each of these which was earlier austenite, they will be perlite. Now, in the same terminology we can use to represent these alloy, that these are called hypoeutectic alloy, hypoeutectic, this side is hypereutectic, and this, as I said, this area is represents cast iron. And what will be the structure of an hypoeutectoid cast iron? Here when it solidifies, you will have some primary grains of depending on the composition where you are, and when that eutectic isotherm is crossed, you cool below the eutectic isotherm, here you will have that leadiboride structure formed. Yes. So, leadiboride structure will form, and as you cool further, this austenite will shrink and some cementite will precipitate out, they will shrink, these also will shrink, and when this temperature is crossed, you will have all these will get untransformed austenite will get converted into perlite, and the structure will look up as you will have primary austenite which has converted into perlite, you will have eutectic, that is transformed eutectic, which will consist of basically transformed austenite which has transformed into perlite plus cementite. So, morphology wise it will be little different. Here also it will be exactly similar, same way you can draw the microstructure. Here you will have primary, these are will be cementite, and this area will be the transform eutectic. So, that means, if you look at the know the phase diagram, it is possible to find out what will be its microstructure, and this microstructure, as we have been as it has been emphasized again and again, that properties of a material is a function of its microstructure. So, the microstructure you will be able to guess the properties, and next class we will see some examples. So, today what we did so far is we looked at the binary iron carbon phase diagram. It is basically iron cementite phase diagram. The cementite, we talked about cementite, which is a metastable phase. We also talked about the crystal structures of iron and how they are known as. So, that is called delta, which is BCC, called ferrite, then austenite, and then we have low temperature BCC structure. We talked about 3 invariant reaction, peritectic, eutectic, eutectoid. we talked about paralitic structure, which is the eutectoid structure, we talked about eutectic ledeborite and transformed ledeborite, and we also saw some examples of how to estimate percentage phases as a function of composition. Thank you.